Yes. So good evening all. So in mass spectrometry, so few selective areas we covered. So now we are going to discuss a new topic in mass spectrometry after knowing types of ions. So we discuss some selective concepts in mass spectrometry, starting from what is a general introduction of mass spectrometry, what are the types of fragmentations are expected, and what is the role of molecular ion, etc. Then we also discuss what are types of ions. Okay, generally in mass spectrometry we have molecular ion, then fragment ion, then even electron ion, odd electron ion, isotopic ion, like that metastable ion, all types of ions we discussed. So today we are going to discuss what are the mass spectral peaks and what are the mass spectral fragmentation or pathways. Then finally what are the rules of mass spectra. Okay, so keep reading. Mass spectral peaks. Mass spectral peaks. So means I would like to write a mass spectra. Okay. So how to write a mass spectra or mass spectral peaks? Right. Mass spectrometry or mass spectral peaks, it is a two-dimensional graph. It is a two-dimensional graph. Write directly. Similar to UV and IR. So UV spectroscopy, IR spectroscopy, how we are writing a graph. Similarly, you will write a graph in mass spectrometry. It is a two-dimensional graph similar to UV and IR. Okay. So it is represented by sharp vertical lines. Sharp vertical lines. We are going to represent by a sharp vertical lines. It is represented by sharp vertical lines. Okay. Along x-axis, embedded values are represented. Along x-axis, embedded values are represented. Then what about along y-axis? Along y-axis, percentage of abundance. Percentage of abundance of ions are represented. So along y-axis, percentage of abundance, intensity, relative abundance is going to be represented. Okay. Along y-axis, abundance, along x-axis, embedded value. Means it is a two-dimensional graph. It is a two-dimensional graph. Here embedded value, this is increasing embedded value. This is percentage of intensity. Percentage of intensity or percentage of relative abundance. Try to remember this point. Percentage of intensity nothing but height. It is also called percentage of relative abundance. Relative abundance means one reference is taken. Means with respect to one reference we are writing the intensities. So this is a sharp vertical lines. You may write in different sizes. These all are called mass peaks. Sharp vertical lines along x-axis, embedded value, along y-axis, percentage of intensity. This percentage of intensity also called relative abundance. Relative abundance means with respect to one peak, other peaks heights will be decided. That is called relative abundance, otherwise percentage of intensity. Both are same words. Percentage of intensity or relative abundance, both are same. Here you can write percentage of intensity or percentage of relative abundance. Percentage of relative abundance. It is a two-dimensional graph similar to UV and IR. It is represented by a short vertical lines. Along x-axis, embedded values are represented. Along y-axis, percentage of relative intensity. Otherwise, you can say percentage of simple intensity. Both are same. percentage of intensity, percentage of relative intensity, both are same. Okay, next. See, mass peaks are classified into 5 types. So there are 5 types of mass peaks are there. Mass peaks are classified into 5 types. 5 types of mass peaks are there. First one, molecular ion peak. Second one, fragment ion peak. Fragment ion peak. Third one, isotopic peak. Isotopic peak. Then fourth one, metastable ion peak. Metastable ion peak. Then last one, base peak. So these are the 5 types of peaks are there. So few peaks and ions already we discussed, that I will give in short. Okay. So generally whenever if you are writing a short vertical lines, that short vertical lines may be any one of these 5. The short vertical lines are any one of these 5. It may be a molecular ion peak, or it may be a fragment ion peak, isotopic peak, metastable peak, and one more is base peak. Like that 5 types of ions are responsible to give 5 peaks. Only 5 peaks are available in separate form, but actually many fragment ions or peaks are appeared, many fragment ion peaks. Okay, then many base peaks are possible. For every molecule only one base peak is possible, many fragment ion peaks are possible, and every molecule having only one molecular ion peak. So first one, molecular ion peak. So what is molecular ion peak? See, if any peak belongs to or any peak which is related to molecular ion, that peak is called molecular ion peak. Always molecular ion peak is appeared at high mass region. Most commonly they are represented at high mass region, but that is not always. Okay, but in generally molecular ion peak gives information about molecular weight of a molecule. It will give information about stability of a molecule. It will also give information about whether it is a stable molecule or unstable molecule, whether they carry bromine, chlorine, nitrogen and sulfur, such elements or not. Okay, that is the information given by molecular ion peak. Means every peak some information is going to be given, that we are learning right now. Okay, so what is molecular ion peak? See, right, the peak belongs to molecular ion. The peak belongs to molecular ion. Okay, so most commonly peak appears at where it appears? High mass region. It is going to appear at high mass region. Already we learned these points. What is molecular ion peak we explained, but what happens right now, what is the use of that molecular ion peak I am saying? What information it will give, that we are going to learn here. Okay, when one electron is removed from molecule, that is responsible to give molecular ion. So that molecular ion responsible to give one molecular ion peak. So what information you may expect for that molecular ion peak? Okay, so peak appears at high mass region, that is called molecular ion peak. So most commonly I am saying, see, this is percentage and this is M/Z value. Molecular ion peak may be a high intense molecular ion peak. Molecular ion peak may be a low intense, or sometimes molecular ion peak may not be appeared. Okay, don't think that always molecular ion peak is a high intense one. That is wrong statement. Molecular ion peak may be highly intense, or molecular ion peak may be low intense. Otherwise, molecular ion peak may be disappears. Anything may be happen. That depends upon the stability of a molecular ion. So this peak intensity depends on which one? Try to give the answer. This peak intensity depends on stability of molecular ion. Suppose if molecular ion is more stable, this intensity increases. If it is unstable, intensity decreases. Suppose if it is highly unstable molecular ion, then it is found to be disappears out. Sometimes you won't expect any molecular ion peak in mass spectrometry. That is 100% depends only on stability of molecular ion. Okay, so here you write that point. C, intensity of molecular ion. Intensity of molecular ion peak depends on, where it is depends? Depends on stability. It is clearly depends on stability of molecular ion. Intensity or relative intensity of molecular ion depends on stability of molecular ion. Intensity of molecular ion peak depends on stability of molecular ion. So as stability increases, what happens? As stability increases, intensity of peak increases. Stability increases, intensity increases. More stable, more intense molecular ion peak. Especially see few molecules, especially bulky molecule or bulk molecules, high molecular weight, bulk molecules, molecular ion peak may be not available. So don't think that 100% it is available. Molecular ion peak may not be available. So few molecules, especially bulk molecules, molecular ion peak may be not available, especially sugars, steroids, alkaloids. This point already explained. So some molecules there is no molecular ion peak. Okay, especially see it is reference for isotopic peaks. It is a reference for isotopic. These statement questions are giving in exam, GATE exam mostly. It is a reference for isotopic peaks. If you want to identify isotopic peaks, what is the reference? Molecular ion. Because after molecular ion, if any peaks comes, that is almost all maximum isotopic peaks only. So that's why it is a reference for isotopic peaks. It is reference for isotopic peaks. Okay, next. Molecular ion peak used to determine mass of molecule. Mass of a molecule. For a given mass of a molecule, if you want to determine, if you know the m by z value, you can calculate. With the help of m by z value of this molecular ion peak, we can calculate mass of this molecule. Because what is the difference between molecule and molecular ion? 1 electron. So we can determine mass of a molecule. Okay, so especially molecular ion, it is used to determine number of chlorines, number of bromines, number of sulfurs. So with the help of molecular ion, we can determine how many chlorines, how many bromines, how many sulfurs are present. It is used to determine number of chlorines, number of bromines and sulfurs. Clear? That is about molecular ion peak. So what is use of molecular ion peak? The key point for molecular ion peak is it is used to determine mass of a given molecule. Molecular weight we can determine very easily. Mass we can determine very easily. It is a reference for isotope. It is used to identify number of chlorines, bromines and sulfurs in a given sample. Okay. Next. Second one. Fragment ion peak. Fragment ion peaks. So if you want to determine stability of any molecular ion peak, that depends upon the what type of molecule it is formed. Okay. Suppose after losing electron, if it is forming an even electron, intensity very high. After losing electron, if it is forms a odd electron, intensity very less. Okay, that point already explained. As stability increases, this point is important for intensity of peak, molecular ion peak. And this is the use of molecular ion peaks. Okay, molecular ion determine the mass of molecule. Source for isotopes used to determine how many chlorines, how many bromines, how many sulfurs are present in a given sample or molecule. Clear? Now. So what is fragment ion peaks? Okay. Now, right. The peaks produced by fragment ions. The peaks produced by fragment ions is called fragment ion peaks. Okay. Next. They always represent left side of molecular ion. They always represent left side of molecular ion. Molecular ion, if it is right side, remaining left side, all are belongs to fragment ion peaks. See, this is a mass spectra. Here MBZ value, percentage of intensity. These are the peaks which are appeared. Suppose if I think this is a molecular ion peak, then what about left side ions or peaks which are belongs to fragment ions? Fragment ion peak. Fragment ion is nothing but the ions produced by molecular ion, or molecular ion undergo successive fragmentation will give fragment ions here. Always fragment ion represented left side of molecular ion. Okay. So if you go through intensity of fragment ions, intensity of fragment ion depends on stability. It is depends on stability. Intensity of fragment ion depends on their stability. Okay, because fragment ion may be more stable than molecular ion. Don't think that always molecular ion is more intense than fragment ion. Sometimes fragment ion is more intense than molecular ion. Sometimes molecular ion is more intense than fragment ions. But always remember, we need to write fragment ion left side as compared to molecular ion. Okay, anything is possible. Like this also you can write a spectra. Here MBZ percentage of intensity, molecular ion peak intensity is very less and fragment ion peak intensities are very high, like this. So these all are left side of this molecular ion. They are called fragment ion peaks. Intensity of fragment ion depends on stability. That is also same. So what is the use of fragment ion? They are represented exactly left side of molecular ion or not? Yes. Then what is the use? What is use of molecular ion? Use of molecular ion peak is, it will give information about the molecular weight. It will give information about how many chlorines, bromines, sulfur is present. It also gives information about reference for isotopes, whether isotope is there or not. Okay. So after knowing molecular ion, first you target molecular ion. Then left side of molecular ion belongs to fragment ion. Then what is the major role of fragment ion? Especially see, it gives information about It gives information about structure of molecule, structure and connectivity in molecule. Structure and connectivity in molecule. What is the structure and what is the connectivity involved in that molecule, that can be determined. It gives information of structure and connectivity in molecule. Molecule structure, molecule connectivity clearly given by this fragmentines. Only one thing is helpful for fragmentine. Fragmentine gives information about structure of original molecule. It also gives information about the connectivity. What type of connectivity is there within the molecular end. That is fragmentines and fragmentine peaks. Next, third one, isotopic peak. Isotopic peaks, ion, or isotopic peaks. Isotopic mass peaks we are learning. Okay, where they are represented? So, isotopic peaks, now, it is belongs to molecule having isotopes. It is belongs to molecules having heavier isotopes. If any heavier isotopes are present, it is going to be represented. If there is no heavier isotope, no isotopic peak. Suppose if any lighter isotope is present, already this point explained, lighter isotope, heavier isotope. Okay, when lighter isotope is present, so there is no isotopic peak. Suppose if any heavier isotope is present, then only isotopic peaks are represented. Okay, so it is belongs to molecules having heavier isotope. Okay, so where it is represented? Now, they are represented right side of molecular ion peak. Okay, na? Yes. So they represent exactly right side of molecular ion peak. If you want to represent any isotopic peak, it is exactly right side of molecular ion peak. So those who completed, you take down that one. Yes. So isotopic peaks, nothing but if any molecule having heavier isotope, so generally that embedded value of molecular ion with lighter isotope, and if any isotopes are included in that one, you will get one additional peak that is belongs to isotopic peak. It is exactly right side of molecular ion peak. So what is the use of isotopic peak? Now generally see, it is represented by isotopic peaks are represented by m+1, m+2, m+3, etc. Okay, so what is the use of isotopic peaks? Used to determine carbons, especially carbons. Which peak will give information about carbons? M+1. M+1 isotopic peak gives information about carbon. This point explain. Right? What is the formula to calculate number of carbons? Formula to calculate M+1 or number of carbons. One formula given. Percentage of intensity of M+1 is equal to number of carbons multiplied by 1.11. Number of carbons is equal to percentage of M+1 by 1.11. So in isotopic peak, generally these peaks are produced by, if any molecule having isotope, then they are exactly right side of molecular ion. Generally they are represented by M+1, M+2, M+3, M+4, etc. Most commonly M+1 is important, which will give information about number of carbons. Yes, next. How many chlorines are present, how many bromines are present, and sulfur can be determined by isotopic peaks. Not only number of chlorine, bromine, sulfur, and whether isotope is there or not, that can also be determined by isotopic peak. Not only number of chlorines. So maybe molecule carry 1 chlorine, 2 chlorine, 3 chlorine. That information given by molecular ion and isotopic peak. But advantage of knowing isotopic peaks, how many isotopes present in one molecule? See here, how many chlorines are present? 2 chlorine. So 2 chlorines may be lighter isotopes. In these 2 chlorines, one may be lighter, other may be heavier. 2 may be heavier. That information given only by isotopic peaks only. Okay. So this is one of the examples. Suppose see, if I take 1 bromine, what do you expect? 1:1 ratio. Suppose if 2 bromines are present, what is the ratio? 1:1. Then 3 bromines are present. 1:3:3:1. So based on this, it is confirms that this M+2, M+4, that will give information about how many isotopic chlorines, bromines, sulfurs are present within the molecule. One molecule may carry many possibilities. One molecule may carry only lighter isotopes. Only one will be lighter isotope, remaining 2 may be heavier isotope, or all may be heavier isotope. So what is the nature of isotope? What is the nature of isotope can be explained by isotopic peak. Okay, how many isotopes and what is the nature of that isotope? Whether it is a lighter isotope or heavier. How many such heavier isotopes? See, chlorine is represented by 37, 35, this is 37. Here 2 chlorines are there. 2 chlorines, 35, 35, 2 lighter, 35, 37. 1 lighter, 1 heavier, 37, 37, 2 heavier. How many such heavier isotopes are present and what is its nature can be explained by isotopic peak. Next, metastable ion peak. So what is the difference between normal ions and metastable ion? This I given in your last class. Normal ion and metastable ion. Normal ions are produced in ionic chamber. Metastable ion produced in mass analyzer. That is the difference. So I can say that the mass peak produced by metastable ion. The mass peak produced by metastable ion. Where this metastable ion produce? It is produced in mass analyzer. That point I am not writing because already you are aware about metastable ion. Okay. So metastable ion is a low intense broad diffuser peak. It is a low intense broad diffuser peak. It is a low intense broad diffuser peak. So it may be non-integer. M star will be written now generally. Already given meta apparent mass is equal to m2 square by m1. What is this? Daughter by parent. Apparent mass is equal to daughter square by parent. So this parent undergo fragmentation in mass analyzer, that will give m2. Now m2 is nothing but metastable ion. M2 is a metastable ion which is produced in mass analyzer. Now whose mass will be taken? M star. This M star is nothing but apparent mass. Okay, generally they are represented like this. This is M by Z value. This is percentage of intensity. These are peaks. Okay, suppose see this is 46.4 I written, in rough example 46.4. Now this is belongs to metastable ion, that is M star. Okay, so here who is daughter? M2 is daughter or not? This is M2. Okay, M2 is a daughter, M1 is a parent. M1 is a parent, M2 is a daughter. So between these two some value we written. This indicates that there is a link between parent and daughter. So this is a low intense broad diffuser peak, that is called metastable ion. This metastable ion produced in mass analyzer. Always it is represented by non-integer value, but don't think that it is always non-integer. Sometimes it may be a integer, but majority cases, most of the cases, this peak is belongs to diffuser peak in mass spectrometry belongs to metastable ion. What is single focus mass spectrometry? Only magnetic field is present. Double focus what? About double focus mass spectrometry, two fields are present, electric field and magnetic field. So what is the difference between single focused and double focused? Single focused resolution is very poor. Double focus resolution is very high. Resolution nothing but ability of separating ions having a same M-Z value but differ in their number of and type of elements. Suppose two fragments having same M-Z value. M-Z value is same, but elements are may be different. Carbon, nitrogen may be present, carbon, oxygen may be present, but M-Z value same. When same M-Z value is present, on the time peak intensity at same place or not? Suppose here M-Z value 28, but element carry carbon, oxygen and hydrogen. Other fragment, what I am saying, that fragment carry carbon, nitrogen and hydrogen. M-Z value same, but fragment elements are not same. So the two elements we are writing over here or not? Can you identify on the time fragment? No. Because same M-Z value is there, we can't identify the fragment. That's why we are using resolution. Resolution means separation. So when two fragments having same M-Z value but differ in their elements, they can be discriminated very easily by using double focus mass instrumentation. So how can you make discrimination? That by using by fraction. Suppose one particular fragment 28 is there, other is also 28, but resolution will give clear information 28.002, then one more 28.2 or 28.3, like that. Means point fraction difference, whatever is observed between the two elements, can be easily discriminated by using double focused. Simply only one thing you remember, single focus means we can separate each and every element but not clearly. Double focus means each and every fragment in mass spectrometry can be separated high end, in a high end. Means you will get a much more gap. So when you go for double focus, you will get more information. That's it. Okay, that is metastable. And go through base peak. These questions I will give later. What is this metastable ion? How to calculate that? But only one point you remember. This ions produced in mass analyzer. That's it. Okay, you remember this formula. What is M star? Apparent mass of metastable ion. What is the difference between apparent mass and mass? Apparent mass means generally whatever you are getting, whatever you are calculated, that is get differ by 0.1 to 0.4. You will not get accurate value. Some difference value you will get. So we are calculating and we are getting some value. Suppose here 65 by 91, 65 square by 91. After doing calculation, one number you will get. Okay, that number and experiment number. Experimentally we are calculating. Theoretically we are calculating on a paper. That number and experimental number both are not same. That is called apparent difference. Some difference, simply remember. The difference should not be considered. You can ignore it. Clear? Next, base peak. What is base peak? The peak having high intensity in mass spectra. In mass spectra, whichever peak having high intensity, that is called base peak. The peak having high intensity in mass spectra is called base peak. Okay. So the ion having high stability, the ion having high stability among variable fragment ions. Fragment ions, that is generally known as base peak. Base peak is that one which is more stable ion. Most stable ion always taken as a base peak. Okay, the ion having stability among, high stability among, you write this, high stability among variable fragment ions is known as base peak. Okay, so base peak may be, which one is a base peak? Base peak may be molecular ion. Base peak may be molecular ion or fragment ion. Anything is possible. Don't think that base peak is always a fragment ion. Base peak may be a fragment ion. Sometimes base peak may be molecular ion. Indirectly I am saying that sometimes molecular ion is a highest intense peak as compared to fragment ions. So this point is important. Base peak may be molecular ion or base peak may be one of the fragment ion. So whichever is more stable, if you compare all factors, that particular ion is taken as 100%. Okay, that is called base peak. Okay, so base peak intensity, base peak percentage of intensity taken as 100%. This is always taken as 100%. Base peak percentage of intensity always taken as 100%. We need to take always base peak intensity as 100%. And the remaining ions intensity we are calculating based on the reference base peak. See, other ion intensity we are calculating on the basis of base peak only. So that's why we are calculating the intensity of other ions based on base peak. That's why base peak is taken as always 100%. Base peak height is taken as 100%. Related to base peak, other peak intensities has been calculated. That's why it is called relative intensity. Relative intensity nothing but we are giving the intensity of isotopic peaks or fragment ion peaks based on the base peak. If you know the base peak intensity and if you assume that base peak intensity is 100%, related to base peak intensity, if you determine the intensity of other peaks, that is called relative abundance. So that's why first we need to target which peak? Base peak. Okay, so with the help of molecular ion peak, or if you consider molecular ion as a base peak, with the help of base peak only other peak intensities are calculated by assuming that base peak is a 100% peak. Here every time you remember, every time highly stable ion is a base peak intensity taken as 100%. And in related to base peak intensity, other peak intensities are calculated. Then that's why that peak intensity is known as, what is it? Relative intensity. So what is the meaning of relative intensity? Relative intensity nothing but we are writing a intensity of a peak with the help of other peak. See, if you compare any examination, you need to compare with your friend. So both are written examination for 100 marks only. Your friend got 90%, you got how many marks? That is called relative intensity. They won't compare about 100 marks. They will compare about your marks and your friend marks only. You written exam, your friend is also written exam. Both people written one examination for 100 marks. You scored 40 marks. Your friend scored 90 marks. Then they will compare for 90 and 40 marks only. They won't compare 100. So that 90 marks is taken as a 100% marks. Okay, 90% marks is taken as 100% marks. That is called gate calculation, and even for IIT G entrance calculation like that. Because whichever person is written or who is a topper in examination, that person is taken as 100%. Suppose you written one examination, 1000 people are written examination. Okay, so question paper carry 100 marks. In that, topper got 92 marks. Topper, first ranker got 92 marks. That 92 marks taken as a 100%. With related to that 100%, other people percentage has been calculated. Not with respect to 100 marks. It is with respect to which person? The person who scored high percentage, 92% calculation. Okay, that is called relative abundance. That's why percentile, it is not percentage. Much more difference is there between percentile and percentage. Even though you got 42 marks out of 100 in gate examination, suppose general example I am saying, out of 100 marks you got 42 marks in gate examination, 42 marks only, but you are 98 percentage, you get 98 percentile. 98 percentile means with respect to topper. Topper got 56 marks means almost all you are in a better range, good range only. Suppose topper got 92 marks, you got 42, no use. Percentage is very poor. So that is the difference. So that's why base peak is very, very important in mass spectrometry. Base peak percentage of intensity taken as 100%. Okay. So in relation to base peak intensity, other peak intensity calculated. Other peaks intensities are calculated or determined. Okay, in relation to base peak, other peak intensities are determined. Okay, so that is generally known as, what do you say? Relative abundance. Percentage of relative abundance. This is percentage of relative abundance. So percentage of intensity, percentage of relative abundance, both are same. So what is the use of base peak? we can determine which is more stable among all fragments. That is only one point. It is a highly intense peak in mass spectrometry. With the help of this base peak height, other peak heights will be determined. Okay. In relation to base peak intensity, other peak heights or other peak intensities are going to be determined. That is called percentage of relative abundance. So one formula is there. Percentage of relative abundance of specific peak. Percentage of relative abundance of specific peak is equal to. Okay. So here I can say height of selected peak by height of base peak. What is height of selected peak and height of base peak multiplied by 100. This is a formula. Height of selected peak. What is the height of selected peak and what is the height of base peak? And if you multiply with 100, that will give percentage of relative intensity. Clear? So this is the mass spectrum. Just you take one example. So this is 91. This is MPZ value 91 and this is 65. And this is 39. MPZ value 39 and here I am taking one more. This is 92. So this is molecular and peak I am saying. This is molecular and peak. Now who is base peak here? 91 is base peak or not? I can say 91 is a base peak. 91 is base peak. Now here I am writing this is that fragment. This is toluene. Toluene MPZ value is how much? 92. If you remove one hydrogen from toluene, what you will get? 91 or not? If you remove one hydrogen from toluene, 92 minus 1, 91. 91 is nothing but base peak. So here this is called tropylium. Tropylium. Tropylium comes from toluene. So this is also belongs to benzyl cation. Remember. Even for benzyl cation, this values remain same. Benzyl cation undergoes scrambling will give tropylium. Benzyl, tropylium both are same. Rupture of CC bond will give tropylium. If you break this sigma bond and if you attach on this carbon, that will give 7-membered ring. That is called tropylium. Tropylium, benzyl both are same. Whose MPZ value is how much? 91. Then if I take a 5-membered ring, this is 65. Then if I take 3-membered ring, that is 39. This is percentage of intensity and this is MPZ value left right. So these are the peaks I given. I want to calculate the height. Okay. So which is base peak here? 91. 91, see, this is suppose 80 millimeters are there. Just measure that millimeters or you can take in centimeters also. Anything you can take. Height of this will be 80 millimeters. And height of this one. This is 40 millimeters and this is 60 millimeters I am taking. Height. This height I am taking. This is 40 and this is 60. And here this is 30 millimeters I am taking. So if I take base peak, so what is the formula for relative intensity? Percentage of relative abundance of specific peak. I am going to take this one. This peak intensity. Specific peak is what? 80. 80 by 80 into 100, how much? 100%. So this is 100% or not? See, if you substitute this in this formula, height of selected peak 80, height of base peak. What is base peak here? This one only. 80 by 80 is how much? 100. 80 get cancelled, you will get 100. Now this peak belongs to which one? 100% peak. 100% peak is called base peak. So whichever is very high in distance, that is not going to be taken because always that is a base peak. Okay, now I am going to take one more. So percentage of relative abundance of cyclopentadienyl cation. This one I am saying. Percentage of relative abundance of cyclopentadienyl cation. Then how to calculate? So it is 40 or not? 40 by 80 into 100. Then how much you will get? That is 50%. So exactly if you assume from year to year 100% exactly middle, this height will be there. So then what is the height difference here? Now it is exactly 50%. 50% in this height will be there. Clear? That is the use of base peak. Who is the reference for other peaks? Base peak only. If you want to write these heights, first you calculate the height of base peak. If you increase the height of base peak, automatically this height also increases. Next, same. Percentage of relative abundance. Cyclopropenyl cation. What is cyclopropenyl cation? This one. We will calculate this intensity. So, what is the height? 60. What is base? 80 into 100. Then how much you will get? You will get around 75%. So with respect to base peak, this height will be exactly how much? This is 75%. Means exactly 80 centimeters, you need to write one line. 40. Then here 75. Height of this peak is related to this one. So based on this we can say which is more stable cation, which is unstable cation. Between tropylium and this one, which is more stable? Between tropylium and cyclopropenyl, both are aromatic. Tropylium and cyclopropenyl cation, both are aromatic. But which is more stable? Tropylium. Tropylium is more aromatic as compared to this one. Like that we can determine based on mass spectrometry. So in examination, if competition comes between these two, which among the following is more stable if they given? You give priority for tropylium. Tropylium is more stable as compared to cyclopropenyl cation. Okay, so this is more stable due to more conjugations. Next, last one, percentage of relative abundance of toluene, molecular and toluene. How much? Calculate and say the answer. 30 by 80 into 100 or not? Is it 30? Height of this 92 is 30. 30 by 80 into 100. How much? Around 40, not, you will not get 40. Around 40 you will get. So 30 by 80 into 100. So this is around 37.5. Okay, so this height is not exactly 25%. This height is more than 25%. So this is around nearly how much? 37.5. So with respect to base peak, this height is 37.5. More than 25%. Exactly 50%, 65, this peak. Exactly 70%, 39. 37 point is 92. But these all cases we are comparing with which one? Base peak. Okay, this 91 we are assuming as 100%. 100% peak. 91 we are assuming as 100% peak. Based on these other percentages we are calculating. Height of selected peak by base peak into 100. Clear? So that is about types of peaks in mass spectrometry. Okay, so right, mass spectral pathways. This is also called fragmentation rules. Before starting off fragmentation rule, pathways we need to learn. Mass spectral pathways or fragmentation pathways. Mass spectral pathways or fragmentation pathways. After this we will see what is fragmentation rules. So fragmentation rule comes from this one only. Mass spectral pathways. Fragmentation pathways. Both are same. Fragmentation pathways. After types of ions, now major area is going to come. Only two areas will be there. What is pathways? What are rules? Then that is mass spectrometry. Clear information about how to identify the fragments. Okay. So generally three possibilities are there. Suppose see, if AB is a radical cation. If it is a radical cation, you will get one radical and you will get one cation. This is a odd electron, and this is called odd electron, and this is a even electron ion, or even electron species. Your wish, you can write anyone. Okay. So what is the meaning of OE? Odd electron. What is the meaning of odd electron? Carry odd number of electrons. Only one independent electron is there. 1, 3, 5, 7 like that. When this fragment undergo fragmentation, that will give one odd electron and even electron. That is your first one. Now second one, AB radical cation, if they given A is a radical cation, B is one more. So this is a odd electron. Odd electron is giving a odd electron, and what about this? This is even electron. So is it a even or not? See, odd electron, even electron, odd electron, even electron. Okay, and here see, odd electron, both are same. When odd electron undergo fragmentation, remember, when odd electron undergo fragmentation, that will give always one odd electron and one even electron. They never give two odd electrons. They never give two even electrons. Okay, then this is called even electron rule. Even electron rule is saying that whenever if I take any even electron species, when I take any even electron species, that will give one even electron and one even electron. So both will be even electron only. Even electron, and here also even electron. This is called even electron rule. Even electron rule. This rule you remember. According to even electron rule, when any even electron ion, when any even electron ion undergo fragmentation, that will give one even electron and other even electron. It is a charged even electron and this is neutral. But neutral and charged both are even electron ions only. Clear? These 2 points you need to remember, especially even electron rule. According to even electron rule, when even electron, I will give the definition. When even electron ion undergo fragmentation, that will give even electron and even electron. Okay? These 3 points you need to remember. Now one more, I am writing a radical cation. Is it radical cation odd electron, even electron? Odd electron. Radical cation, when they undergo fragmentation, remember, that will give radical, that may give cation. When radical cation undergo fragmentation gives radical and cation, radical is a odd electron, cation is a even electron always. This one, odd electron, even electron, odd electron, even electron. Here radical and here odd electron. Same statement matching. This one the same. This one same. Radical cation undergo fragmentation gives radical cation. Plus is nothing but what? Cation. Then second possibility, radical cation undergo fragmentation will give radical cation plus neutral. What is radical cation? Odd electron. Radical cation is a odd electron. Here it is a radical cation or not? Is this two or same? No, they are not same. And here see, radical cation, here also radical cation, odd electron, and what is this? Even electron. Okay? So, suppose if I take even electron rule, if I take any cation, cation is what? Even electron. Cation is a even electron. When cation undergo fragmentation, you will get one cation plus one neutral. So, cation is a even electron. Neutral. Every neutral organic fragment is a even electron. So, is this 3 are matching with this 3 or not? Both are same. This and this both are same. Some books they will write like this, some books they will write like this, both are same. So what about third one? Third one is very, very important one. Third one is called even electron rule. It is there in your syllabus separately. Even in your textbooks also they will explain what is even electron rule clearly. So what is use of these pathways? Only these pathways are allowed. Remaining are not expected. Remaining fragmentations are not considered. You can ignore it, that one. Only if they follow these 3 rules, only that fragmentation is accepted. You write 1 point for even electron rule. Keep heading even electron rule. Even electron rule. Right. According to even electron rule, according to even electron rule, according to even electron rule, fragmentation of even electron ion, fragmentation of even electron ion produce two even electron ions. Fragmentation of even electron ion produce two even electron ions. Okay, that point you remember. Whenever if it is an even electron, you will get two even electrons only. You will not get odd. So don't think that when odd is given, they will give odd. Okay, when odd electron species is given, don't expect both will be odd. When even is given, both will be even. Already explained types of ions: molecular ion, fragment ion. Next is what? Even electron ion, odd electron ion. One formula given, right? When even electron ion, odd electron ion both are present, which is more stable? Even electron ion. Odd electron ion is unstable. And even with nitrogens also explained. Without nitrogen, with nitrogen. Even electron ion, even number of electrons. Odd electron ion, odd number of electrons. So one point I explained. So here if I use the word ion, even electron ion, nothing but even number of electrons. Okay. So here one fragmentation I will explain. See this. So this is your first fragmentation. This one I am saying. Okay. See, if radical cation undergoes fragmentation, if any radical cation undergoes fragmentation, produce what they produce? Radical and cation. Only this fragmentation is observed. That fragmentation is correct. That's what I am saying. Only that fragmentation is correct. If radical cation undergo fragmentation will give radical and cation. Is it radical? Then what is this? Cation. So radical is a odd electron. Cation is a even electron. Both are same. Okay. Now see one example. Suppose if I take benzene, this is benzene, radical cation, double bond, double bond. Okay. So is it an even electron or odd electron? Odd electron, because see 1, 2, 3, 4, 5. 5 electrons are delocalizing. So it is a odd electron ion, odd electron ion. Now when odd electron ion undergo fragmentation, what is your answer? When odd electron undergo fragmentation, it will give one odd and one even. And one more, one radical and one cation. What they produce? Radical and cation. Suppose if you break this bond, here one radical is left or not? Now this radical bonded together. If these two are bonded, here you will get positive charge. And what about hydrogen? Hydrogen will be in the form of radical. Then what is this? Odd electron undergo fragmentation to give cation and radical. Is it odd electron? If a radical cation, odd electron, undergo fragmentation will give cation and radical. Means I am saying that this fragmentation is correct. That only the 3 rules we need to follow for every fragmentation. If you follow the fragmentation rule, then only it is correct. So whichever direction you want to break fragmentation, that won't exist. You follow the 3 rules. If you know these 3 rules, answer is over. This first one we are applying right now. If radical cation undergo fragmentation, that will give radical and cation. Radical and cation. Now this fragmentation pathway is correct. Right? Is it right or wrong? Right. See, this is one molecular ion, toluene I am writing. This is radical and this is cation. and here I am writing CH2H. Is it a odd electron or even electron? Odd electron. This is a odd electron. Now this odd electron undergo fragmentation over here. Then what happens? This radical, you will get double bond, right? So when you get double bond, and what about this? What is left here? Cation. And what is this? Plus. Hydrogen radical or not? This is removed in terms of radical. Hydrogen radical CH2. This radical double bond. What is this? Is it a cation? Then what is this? Radical. Cation, radical. Then what is this? Is it a radical cation? Radical cation. Radical cation, cation, radical. This fragmentation is correct. You came to know which is correct, which is wrong clearly by using this technique. Whichever fragmentation you want to do, that fragmentations are not exist. Only by following some rules, we need to write the fragmentation. These three pathways you need to remember permanently, so that in mass spectrometry if any question comes based on these three only, we are writing the fragmentation modes. Now see, this is CH2 and this is hydrogen. Here this is CH, carbon double bond. Suppose see, if I write radical double bond is there, this is radical and here cation or not? After removing one electron. Is it a odd electron or even electron? Odd electron. Is it a radical cation? It is radical cation. Now it is undergo fragmentation over here. Break this. This radical. See, this radical forms double bond. If they form double bond, what is left on this carbon? CH2 plus. And what about this hydrogen? This hydrogen in the form of radical. What is this? This is cation and what is this? Radical. Following the rule? Yes. Means you can break this bond. There is a meaning. Right. If radical cation, second point I am writing, undergoes fragmentation, what they produce? If they undergo fragmentation, that will produce radical cation and neutral species. Radical cation and neutral fragment. This one, second. When any radical cation is given, you can break such a way that they will give one more radical cation and one neutral will be removed out. This is CH2CH and here X radical cation, radical, and here I am writing hydrogen. Suppose see this. Is it a odd electron or even electron? Odd electron. See, only one electron is there here. Here paired, here also one pair. This is not a pair, only one electron is there, so I can say it is radical cation. See, here I am doing heterolysis and here I am doing homolysis. Then here what you will get? Here radical and here positive. So if I write radical and positive here, this is radical and what is this? Positive. Here positive, here radical. And what about this one? If you add this electron over here, then become neutral or not? And here already one electron is there. This electron hydrogen get combined together and forms HX or not? HX is neutral. HX neutral or not? And what is this? Radical cation. Radical cation and what is this? Neutral. Radical cation neutral. So I can remove hydrogen halogen very easily. Dehydrohalogen possible. That is the statement is saying. I can remove hydrogen halogen adjacent or from large distance so that I can remove HX. So same example I am giving one more. This is one carbonyl group. This is CH3. Here this is radical cation. Is it a odd electron or even electron? Odd electron or not? So now I am breaking over here. See, this is homolysis and here also homolysis. Then what happens? Here what you will get? Is it a neutral or radical? Here one radical is there and here also one radical is there. This radical added here. Then what you will get? pH CH2. This oxygen carry radical cation. Lone pair here one radical is there or not? This radical and hydrogen radical both combine together and forms a bond. Then what is this? Radical cation. Now here what is left here? Radical and here one more radical. Radical combine together and forms CH2 combined with this carbon and this is combined with this two. So what is this? This is radical cation and what is this? This is neutral. Radical cation neutral, here also radical cation neutral. It is also possible. Clear? So this is a radical cation. Radical cation. Is it cyclohexadiene? Hexene? Yes. Now what happens? Here I am breaking one bond, here I am breaking one bond. What happens? Is it radical cation or not? If I break here this radical, double bond or not? This radical, what you will get? Double bond. This radical, you will get double bond. A radical and this cation. What is this? Radical cation, and what is this? Neutral. So this is retro-Diels order. Retro-Diels order is possible. Means whether our fragmentation is right or not, whether we are doing correct or not, that can be confirmed by using these methods. Just listen. Is it a odd electron? Is it odd electron or not? Yes, it is odd electron. Otherwise you can say radical cation. Now here I am breaking. If I break here, and if I break here, and if I break here. If I break here, you will get one radical. Here one more radical. Radical, 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 radical. Right? This radical, you will get double bond. This hydrogen migrates from here to here. So if it is migrates, you will get OH, radical cation, lone pair asterisks, right? This dot will take this hydrogen. This dot will take this bond, form double bond. This radical cation asterisk. Right or not? Then finally what is your answer? Radical cation, and what is this? Neutral. McLafferty rearrangement. This is called McLafferty. Pyrolytics in elimination also, same concept. Norris 2. Same one. It is also called Norris 2 under photochemically. So whether this fragmentation is right or not, you can confirm based these techniques. See, it is a radical cation, odd electron species. It is giving a enol and ene. Enol and ene means McLafferty rearrangement is correct. McLafferty fragmentation, Norris type 2 reactions are correct based on this method. Right? Right. See, if even electron species undergoes fragmentation, so what they produce two even electron ions or two even electron species. Otherwise you write one cation and neutral species. This is your third rule. Right or not? First what I am taking? Cation. I am taking cation plus neutral. right? When cation undergo fragmentation, that will give one cation and one neutral. This is even electron. Even electron cation, even electron neutral. If even electron species undergo fragmentation, that will give one cation and one neutral. This is also very, very important because two events you are getting, two fragments are more stable. Yet this is stable, this is unstable. Suppose if any molecule having CH2 unit want to remove out, this is one fragment. Here any radical is there in this one? No, no radical. So I can say it is a even electron ion, also called cation. Now this cation undergo fragmentation, heterolysis. If I remove this, then what happens? See, CH3, CH2 plus, and there is a formation of a carbene. Now this is cation and what is this? Neutral, no charge. One cation undergo fragmentation to give cation and neutral. Clear? Suppose if I take this molecule, now this is benzene. What is even electron or cation or any radical cation? Cation, it is a cation, even electron. This is undergo fragmentation, see this. Here I am breaking this bond. If I break this bond, this radical become triple bond. So there is a formation of triple bond. Then this radical forms how many member ring? 4-member ring. And here what is the charge? Positive. Right? So is it a neutral? Then what is this? This is cation, even cation. Right? Is it even electron or odd electron? Even electron. Even electron fragments give neutral and cation. This technique is very, very important for fragmentation of any functional group. If any pure cation is available anywhere, be careful that pure cation always give one neutral and one cation. Pure cation. This is tropylium, comes from benzyl cation. Double bond, double bond, double bond, and this is cation. Is it tropylium or not? So is it a cation? Yes, it is cation. Even electron ion. Even number of electrons are present. So I can break here. If I break, here what you will get? Triple bond. Triple bond, and if I join these two, how many member ring you will get? 5-membered or not? This is 5-membered. What is this? It is neutral. And what is this? Cation. Cation undergo one more time fragmentation. See, it is a cation or not? This cation undergo fragmentation like this. Then this carbon, you will get one triple bond. This carbon, if you join, what you will get? A 3-member ring like this. So, what is this? It is neutral and this is cation. See, cation, neutral cation, cation, neutral cation. Suppose if any possibility is there, this cation undergo further cation neutral fragmentation. If possibility is not there, never undergo fragmentation. Clear? Like this fragmentations are possible. So that is about fragmentation pathways. Only these 3 fragmentation pathways are there. If you remember this, mass spectrometry is very easy for you. Where to break, it is very easy. Is it even electron and odd electron? Even or not? Yes, it is a even electron cation. Now if you see, if I do heterolytic fission here, heterolytic fission, then what will you expect here? You will get CO in the form of cation or anion. CH2 is removed in terms of cation. See, this is CH2 removed in terms of cation, and what about CO? CO is removed in terms of neutral. Now it becomes a cation, and what about this? This becomes a neutral. That's it. Decarbonylation, loss of carbon monoxide. Clear? So that is about mass spectral fragmentation pathways. So 3 rules are there. One, odd electron plus even electron. Radical cation plus neutral. One more is cation undergo fragmentation to give cation and neutral. So according to even electron rule, when any even electron ion undergo fragmentation, that will give one even electron cation and one neutral. Otherwise 2 electrons having a even electron species, or 2 species having even number of electrons only. Even electron rule, odd electron rule, both are not same. Odd electron rule is saying that when odd electron consisting molecule undergo fragmentation, that will give odd plus even. Okay, but when even electron species undergo fragmentation, that will give even. That's it. That is called even electron rule. So don't compare odd electron rule and even electron rule. Don't think that even electron will give even, odd electron will give odd. That is wrong. Okay, so that is about mass spectral pathways. In your next class, you will see what are fragmentation rules. So by using these 3 rules, so major functional groups, how they will undergo fragmentation, that I will explain. Then we will see individual functional groups. Okay, we'll stop here. You can leave now. Tomorrow same time.